Think we're live. Let's pause that. Okay. So, welcome to June live stream. Let's see. I see 6 of you are here. All right. Let's start with the questions. All right. So, let's see. Ellis Greger had a question about hydrogen fuel cells, particularly fuel cell cars, which were kind of like a really big deal back in the 90s. Everyone was like, oh yeah, let's do this fuel cell stuff. And then they just kind of disappeared. And it says they looked and found that Honda and Toyota have recently released fuel cell cars, but not a very wide release. And there's a reason for that. It was kind of an exciting thing up front. It was like this space age technology, and everyone kind of, it was very easy to market. But the problem is that fuel cell technology isn't very efficient when it comes to cars, right? I mean, we can use this on like the space shuttle or something, but on a car, not so much. There's a lot. There are a lot more issues, right? I mean, you've got air resistance and stuff like that. And so that can cause some problems, which you don't have that in space. But the main obstacle there is that you have to be able to fill up your car with hydrogen gas. And that's not exactly something that's easy to create and transport and store places. It's kind of dangerous, right? It's extremely flammable. And so you kind of have to watch out for that. It's also not cheap to do any of those things, and it also requires energy, right, to move it around. Electric cars are much better, right? They aren't as exciting as fuel cells, but they are already set up to sort of fit in with the grid that we already have in place, right? We already have electricity being delivered to all sorts of places, and it's super easy to just install a plug for someone to plug their car into, right? I mean, Tesla's been doing this in a variety of places, setting up, charge stations and stuff. So, it's not, right, there's other things to consider, right? Infrastructure to consider. It's not just about the car. And so there's a lot of factors. And so, like, while it was exciting when it first came out, it didn't really pan out. What the heck is a fuel cell? Yeah, so if you've never heard of a fuel cell before, it's kind of I don't know if it's the best name, but basically, at least in a car, right? You'd have to fill up with hydrogen and use the oxygen from the atmosphere. And what it does is it pumps both gases through a fuel cell. It's kind of like a big mesh plate, several of them actually. I could do a whole video on fuel cells, but I'm not going to go into the details here. But the point is that it pumps both of these gases through the cell, and in the process, right, it turns the hydrogen and oxygen into water, and in the process, you get energy out of it. And so it can take the energy and use it to move the car forward, and the only byproduct is H2O. It's water, pure distilled water, basically. And so it's very, very clean, extremely clean. But again, that's just the car, right? You also have to consider the energy in moving the hydrogen around and storing it places, and that is probably done by larger trucks, which maybe the fuel cell technology doesn't work for, and so then that's being, transported by a gasoline powered vehicle, and so, like, there's a lot that goes into making something clean. So while the car is clean as far as like clean energy goes, um, the entire process might not be. And so, uh, anyway, that's what a fuel cell is. It just takes hydrogen and oxygen gas and it turns it into water to release energy. Says electric cars are all good in places where energy comes from renewable resources, right? Yeah. So again, you've got to consider, the cost of getting the, even for electric cars, you've got to consider the cost of, like, well, where is that energy coming from? And so around my area, for example, in the Metro Detroit area, we're talking coal mostly. And so at that point, you're filling your car up with electricity that was generated by burning coal. Now, that's still less than what a gasoline powered car does, right? It's not perfectly clean like everyone thinks it is, but it's still less because then the energy generation is sort of more localized, right? It's not spread out through all these vehicles and stuff. So there's a lot to go into there. In fact, Real Engineering does videos on this stuff a lot, where he sort of considers all the different factors, the infrastructure and transport and stuff. And so if you're not familiar with Brian's channel, you should check that out. If you're into this engineering type stuff. Oh, hey, Tommy, glad you made it. Okay, so next question here. Let's see. I'm Korg. This is Meek. Says, what the heck is strange matter? Strange matter is something that we may or may not find in the cores of neutron stars, but it requires a lot of gravity to generate. Now, I should say that the basic idea behind a neutron star is that it's mostly made of neutrons. There are some protons and electrons floating around, particularly in the outer layers, which is why they have magnetic fields. But the deeper you go, the more and more dense the matter gets. And so eventually you just get to a point right near the center where it's just neutrons. And the density down there is basically on the level of an atomic nucleus. And so you can almost think of the core of a neutron star as being like a big astronomically sized atomic nucleus, which is kind of wild. But if a neutron star is large enough, it is massive enough, then the gravity in the core could be strong enough to overcome the neutron degeneracy pressure a little bit, and that's the pressure that holds it at bay. It holds gravity at bay and keeps the neutron star from collapsing. And so somewhere near the transition between neutron stars and black holes, you might get something called a strange star, where some of the neutrons in the core have collapsed under their own weight and they're not neutrons anymore. And in the process, they become up and down quarks, just a big soup of up and down quarks, which is something that we haven't seen like in a normal universe situation since like the early universe, the first few fractions of a second. But there may be enough gravity inside of a neutron star to create this. And in the process of crushing the neutrons into up and down quarks, some of them could very easily decay into strange quarks and find some kind of like intermediate stability, some stability in between a typical neutron star and a black hole, which is kind of interesting, but we don't tend to observe quarks by themselves, and so it's kind of hard to test exactly what what that would look like and how it would behave and whether or not it could actually exist. And that's not typically something you would find outside of a neutron star, right? If two neutron stars hit each other and matter got flung out, you probably wouldn't get any chunks of strange quark soup floating around the universe. The lack of pressure on them would make them turn back into neutrons or whatever. And so it's kind of an interesting thought, but there's really no way to test it at this point. We'd have to get to larger energies and particle accelerators, and that's kind of tough. So it's kind of a cool idea, but nothing we really need to worry about. All right, so let's see here. William Morton wants to know the relationship between frequency, wavelength, energy, and momentum of a photon. In particular, how that relates to lasers and their wattage and wavelength and so on. Now, the question says a 10 watt, or let's use probably more realistic units, 10 milliwatt, 445 nanometer laser, it says is considered to be the same energy as a 20 watt or 20 milliwatt 880 nanometer laser. I don't. Well, first of all, wattage isn't energy; it's energy per time. It's a power. It's not typically an energy. In order to get an energy, we'd have to have a continuous beam running for a certain amount of time. But it's the power output of the laser, and that should not depend on the wavelength. A 20 milliwatt laser, regardless of wavelength, should be twice the power output of a 10 milliwatt laser. It should be independent of wavelength. Now, there might be something you might have read about how the photons that are coming out of the laser, I mean, those definitely have a very particular wavelength, which is very different from how a incandescent or fluorescent bulb works. But they do have a particular wavelength of light, right? So what these lasers do typically is they take advantage of the specific substance that's in the laser. And so if we're talking about a gas tube laser, it's the standard one is like the Heine laser or helium neon laser. And so it takes advantage of helium gas and neon gas inside of a tube to generate light. Now, these two atoms only work together like that for a particular type of photon, a red photon of a specific wavelength. And so when you get the gas working the way that it does to make your laser, then it is putting out a very specific wavelength. And the same goes for any other laser that you might see, particularly the gas tube lasers. But what the wavelength of the light is can affect things like photon density coming out of the narrow opening on the front of the laser. But it shouldn't affect the power output. If the laser says that it's 20 milliwatts, which is quite a lot of watts, by the way, then it should be 20 milliwatts. And all different lasers, you could have a red laser and a green laser and a blue laser, and if they're all labeled 20 milliwatts, they should all have the same power output. But that wavelength does come into play when we talk about like the colors that are coming out and how many photons there are per cubic meter or cubic centimeter or millimeter or whatever. So a lower wavelength laser doesn't need as many photons to reach the power output, right? Whereas a more red end, a higher wavelength laser requires more photons to come out of the laser in order to get that power output. But it shouldn't be true that the wavelength and power need to be used together. That doesn't make sense to me. But like I said, lasers do work differently than bulbs, right? Whereas a laser puts out a very particular wavelength, the the a typical bulb, a light bulb, puts out all the wavelengths in of various brightnesses, but um, there is a peak wavelength, which for a typical indoor house bulb, we're looking at like yellowish white, right? But it is emitting orange and red and blue and violet and all sorts of other invisible light at you know a bunch of other wavelengths, because those are just based on things like temperature and stuff. But lasers are very specific, and that makes them useful for things. But um, either way, the wattage should determine the power output regardless of wavelength. So um, can only inert gases be used for lasers? I don't think that's a restriction. I think all that really matters is how the atoms, interact with each other. But I'd have to look into it to be sure. I kind of avoided graduate level optics, so I didn't get to do the actual like laser experiment. There's this one lab that they have you do in that class where you have to spend basically just 3 weeks just aligning laser mirrors, and it's the most annoying thing ever. It was a little too practical for me. I was going into theoretical physics, so it didn't really suit what I was doing. But I know some friends who took it, and that was probably the most annoying thing they did in there. But it means that I'm a little less familiar with sort of the engineering aspects of lasers. Let's see. Um, let's see here. Vittorio asks about the imperial unit system, which is the system we have here in the United States. We're one of the few countries that actually use this system anymore. It was the sort of British imperial thing, right? So the British Empire was this, spanned the entire globe, and the United States was sort of a member for a little while, and so we were using those particular units. And by the time the say like Europe, by the time Europe was starting to switch over to the metric system, the United States had already like declared its independence, and we're kind of stubborn. Even now, we're kind of stubborn. But the whole idea was, oh, we're not gonna switch with those people. Kind of attitude. Don't even get me started on it. But so we use imperial units here in the United States: miles, feet, that sort of thing. Slugs for mass, although I don't think anyone really uses that anymore. Kilowatt hours for energy usage instead of joules, that sort of thing. And so Vittorio's question is, how much trouble is it learning scientific formulas and concepts? Well, not actually that difficult, because, well, one, typically when you're going through a science class, even in the United States, they use the metric system, right? Even my, all the way through all of my physics classes, it was the metric system in there, and I just had to kind of get used to it. I wasn't familiar with any of those units, but you get used to them after a couple weeks in your first physics class, and then you're fine. It's not a big deal. And so the metric system is used in typical science classes: physics, chemistry, biology, that sort of stuff. They all use the metric system. It's a very, very convenient system of units for science. Now, the place that you might run into imperial units would be engineering. classes. Engineering people, they're a little more practical, and so they tend to use the more imperial units than the metric system. I think they get used to using both, but they are taught formulas in the imperial unit system in feet and miles and that sort of thing, on pounds for force. And so when they're measuring something like, work done or torque or something, they would use foot pounds instead of Newton meters. And so it gets a little weird, but I don't think it's any more difficult. Units are kind of arbitrary anyway. The only reason the metric system makes sense to us is because our entire number system is based on tens. And so if we have a unit system that's also based on tens, it works really well together. But we don't have to use those units. I mean, there's a lot of, they're, like I said, they're all arbitrary anyway. We made them all up. And so in engineering, if they're learning if they're taking a class that's heavily imperial units, then they're going to learn different formulas that are in imperial units, right? Than they would the ones that I learned in physics, where you learn it in the metric system. And so it's just a different formula, and it's about the same amount of work either way. And so it just, it's just a different way to look at it. I don't think it's any harder. You don't get, the problem with the imperial system is you don't get any of the like automatic relationships between things, right? It's not easy to know how a foot relates to a mile and so on. Or cups in gallons or whatever we're talking about. And so that can be an issue. But as far as the formulas go, the scientific formulas and engineering formulas, they're basically about the same amount of work. Although there is a pretty good argument for Fahrenheit. It is kind of convenient to have a system of temperature that where 0 and 100 are, mean sort of what you expect, right? You expect 0 degrees to be cold and 100 degrees to be hot. Yet neither one of them is going to kill you anytime soon. So that, I think, I could hear an argument that makes more sense to, the average person in society. And so I could hear an argument for Fahrenheit, but otherwise, I mean, I don't even know. I could rant for 3 hours on what units we should be using, and I don't want to eat up the entire live stream on it. But yeah, so it's about the same, I think. I don't think there's a huge issue. All right, so one more question, and then we'll open it up here. Let's see. Someone named Kees von Prusian. I'm terrible with names. I apologize. Kees asked a question about quantum interpretations, quantum mechanical interpretations, something I avoided in my last video. In particular, Kees wants to know about two interpretations, one by Roger Penrose and one by Gerard Tooft, I think is his name. And how they sort of, they sort of compare and contrast. And so just to give you an idea of what we're talking about here, right? So in my last video, in the photons, entanglement, and the quantum eraser, I mentioned that these things were just a model, right? That we model photons as a probability wave. But whether or not those photons actually are waves of probability quantum mechanics doesn't really care what the answer to that question is. It just works regardless. But for whatever reason, our brains need some kind of explanation as to why this model works the way it does. And so we come up with interpretations. And there are a lot of different ones. Pilot wave theory is pilot wave, I should say, the pilot wave interpretation is pretty popular. But the one from Penrose and the one from Tooft doesn't get they don't get talked about very much. I'm not sure why, but as far as Gerard Tooft is concerned, he thinks that the model that we have, this quantum mechanical model, is incomplete. He thinks it's incomplete, and he acknowledges Bell's theorem in particular, that as we look at things now, Bell's theorem says that if you want things to work deterministically, if you want them to have all the properties they're supposed to have, and it's just us unable to measure them, then you have to give up something that we hold very dear, and that is locality. Right? We like anything that affects an object here to be here. Right? We don't like to imagine that some object here is being affected immediately by something that's on the moon or, in another galaxy or something. And in order for particles like photons and electrons to have all the properties that we can't measure about them, then we have to give that up. We have to give up locality. And that's a big problem, right? We would prefer to keep locality and just have things be weird, which Tooft does not subscribe to. As far as Tooft is concerned, underneath quantum mechanics, there is an objective deterministic reality. This is something that he is very passionate about. And he thinks that the problem can be solved by something that we call superdeterminism, where basically absolutely everything in the universe is predetermined to do whatever it's going to do, including us, right? And so we think we have free will, but we don't, right? And he thinks if you sacrifice that, if you sacrifice free will, the ability to choose, then that level of determinism that we call superdeterminism fixes the problem. So then we can actually have local causes without violating Bell's theorem. I'm not sold on that, but it is a thing that he thinks, and so that's sort of Tooft's interpretation. And I don't know if I can subscribe to that, but it is an opinion, and some people get behind him. As far as Roger Penrose goes, his I found kind of interesting. His idea was an attempt to sort of bring general relativity into quantum mechanics, and it isn't like well hashed out. There isn't a lot of actual content there that he could publish in a paper, but his idea is that whether or not an object is in a superposition of multiple states, like it is in quantum mechanics, or it's only in one state, like, say, the human body, for example, depends on how much warping there is in space-time, right? So he pulls in the warping of space-time from general relativity, and he says, okay, well, if things warp space-time only just a little bit, just a smidge, then they're allowed to be in these superpositions of states. Whereas if they're large, if they're like a normal thing, like maybe anything from like a dust particle up to astronomical scales, if they're that large, if they're normal scaled objects, then they can't do that. Then that the amount of energy required for them to warp multiple locations in the universe, it's just too much energy. And so the space-time itself forces them to be in, say, one location at a time. Which it's kind of an interesting philosophy, but again, there isn't a lot of math behind it, and trying to combine general relativity with quantum mechanics tends to not work. And so, again, none of these things are verifiable. Quantum interpretations cannot be verified. They can be disproven sometimes, right? Bell's theorem is an example of something that disproves a whole collection of interpretations, but we still got a huge chunk of them that all sort of disagree that could possibly be true. But in the end, it doesn't actually matter. And so most people at this point, I think Keith wants to know too, is what exactly is my personal opinion on this? I try not to think about it too much, but I like the idea that there's some kind of inherent randomness or vagueness to the universe on some level. I think it allows for things like freedom of choice, for free will, and I like the idea that I have the freedom to choose things. And so I lean toward that. I like that there's randomness down on some level. But I also think that the reason quantum mechanics is so weird, the reason the model predicts really weird things, is because we've reached the limit of what mathematics can actually do, right? And if you've watched a bunch of my videos, you know that I don't think that math is the language of the universe. I think that it's a language of humans. We've made up a language, and it's pretty ordered. And so, the universe is pretty ordered, and so they can correlate a little bit, and it gives us some ability to make predictions. And so quantum mechanics does that as well. It makes incredible predictions, at least for the things it's capable of predicting. It is not capable of predicting all of the things that we'd like it to. But I think that the reason we were forced into statistics and probability is because that type of math always works. It can always get you something. And I don't think that there is any other math that will describe quantum events any better. And so I think we've reached the limit of what math can do, and we're stuck. And that's okay. We just have to kind of acknowledge that we're stuck. I would like to be proven wrong, I think, but it's sort of where I sit on this. So on that note, wow, those questions were involved. All right, so let's open it up here to the chat box. We've got, whoa, Tommy, calm down. All right. So strange matter is never made on Earth. No, I don't think that it is. I've never read about it being made here. It is theoretically possible, but I don't think that we've actually ever made it. It requires a lot more than we're capable of doing. All right. So let's see. Let's see some questions about lasers here. Let's see, black holes. All right, so question about black holes here. I'm not sure where you read that they didn't have mass. They definitely have mass. In fact, anything that gets pulled into in a black hole, gets pulled in past an event horizon, is gonna look like mass, and including light. Mass and energy have a lot of overlap. But no, black holes definitely have mass. What sort of physical condition that mass is actually in, we have no idea. General relativity says it collapses to a singularity, but we don't actually know that for sure. We can't see anything beyond the event horizon, and so we can't know. And so I think that sort of takes care of several questions here. All right, speaking of the event horizon, right, black holes themselves, what's actually in there, what that mass and energy is and how big it is not really important anymore. Once the event horizon forms, we refer to the event horizon as the black hole, even though the event horizon isn't like a solid surface. It's just a place in space. Just like this is a place in space and this is a place in space. The event horizon is a sphere of places in space. And if you were to fall into the black hole, you wouldn't notice probably. You would just keep falling and you wouldn't even notice you crossed the event horizon. It's just a place, right? Just like driving through an intersection, right? And so that can grow because as mass and energy falls into the black hole, the curvature of space-time gets stronger, and as it gets stronger, the place that we can't see past, comes outward and it approaches us, and includes more and more space inside of itself. But it's just a place. It doesn't actually it's not something physical that's growing. It's just a curvature that's getting stronger. Let's see, can you fit an 8-foot pole in a 5-foot barn? I mean, this kind of goes back to my, it's sort of one of those special relativity paradoxes. It's not really a paradox when you actually consider all of the possible factors, right? But just like most paradoxes. But basically the idea is if you run with a pole that's longer than a barn, but you run fast enough, length contraction should shrink the pole so that it actually fits in the barn. And it does. I mean, this is a physical thing that actually happens, at least for one observer that might be standing still next to the barn, right? They're going to see the front of the pole and the back of the pole be inside the barn at the same time. This is a thing that they will observe. And so if you run fast enough, 8 feet could shrink to 5 feet, but the speed at which you would have to run is we can't do that. Like, I mean, human beings, we have an upper limit to how fast we can run. And it certainly isn't going to be like 80% the speed of light anytime soon. So, I mean, it's just, I'm not sure if 80% the speed of light would actually shrink 8 feet to 5 feet, but I'd have to sit and calculate. I don't really want to, but you could very easily calculate it. All you need is the ratio between 8 and 5. So it's like 5 divided by 8, right? 5/8. And then you just set that equal to the relativistic, right, gamma factor, the Lorentz factor, and you solve for V. It's pretty straightforward. Let's see here. Let's see. Attitudes of planes is also in. Yes, altitude of planes is also in feet worldwide. Really, 30,000 feet is like a standard. I didn't know that. That's kind of cool. Units are weird, and decisions that societies make are weird. We'll come around eventually. I mean, technically, we already did switch in the U.S., but we did it sort of under the hood. We didn't do it out in public. So, and I don't see us changing anytime soon. It's just not going to happen. I think engineering uses imperial largely because American manufacturing. Yeah, so there's actually this story. I'm pretty sure I told it in one of my videos, but basically, there was this Mars polar lander that crashed, and we couldn't figure out why it crashed. And eventually, after like a week of playing around, we figured out that Lockheed Martin had designed things in terms of pounds for force, and NASA had done things in terms of newtons, and the several $1 million spacecraft crashed into the polar ice cap because of a failed unit conversion, lack of communication. And so it's definitely something to watch out for. But yeah, so lots of engineering departments at a lot of companies will use imperial units in the U.S. in particular, and so we would be doing engineering students a disservice if we didn't teach them imperial units and the formulas for them. So we're kind of stuck in it. Let's see. Particles being zero-dimensional points with no volume doesn't make sense. No, but I mean, there's a lot of things in quantum mechanics that don't make a lot of sense, right? That don't match our preconceived notions of the world. But the thing is, we don't actually know that they're zero-dimensional points. All we know is that their diameter is less than 10 to the negative 18 meters, right? Because that's the smallest that we can measure. We've done particle collisions and particle accelerators, and we have found that if any of these particles do have size, then we know from our data that it is less than that number, that it's less than 10 to the negative 18 meters. And that measurement, 10 to the negative 18 meters, is 1,000th of the diameter of a proton, roughly. And so it's very easy at that point to just say, you know what, let's not worry about whether or not these things have size. It doesn't really matter right now. Everything else that's happening is 1,000 times larger. So let's just call them points and move on. And so that's basically what we do. We assume that these particles are points because it's easier. We don't actually know that they are. And so that's just something very important to keep in mind when someone says they're point particles. They're approximately point particles. We don't actually know for sure how big they are. Let's see. If space actually has many dimensions, more than width and time, maybe locality is not actually what we think it is. Well, even if there are extra spatial dimensions like the string hypothesis, the string theory would have us believe, locality is still a thing, right? And I mean, there's ways of imagining things like entanglement, things that communicate faster than the speed of light. There are some ideas that maybe that these entangled partners are somehow connected to each other through like a microscopic wormhole, so that they're basically right next to each other, and that they don't have to actually communicate faster than light because, as far as they're concerned, they're not separated by a large distance. They're separated by a very small distance, and so there are always ways around this. But even if there are extra dimensions, there should still be locality. Things should still not go faster than the speed of light, right? So even in string theory, the speed of light is still the universal speed limit. String theory includes general relativity, and that is a very founding principle of general relativity. So having extra dimensions shouldn't affect that. It will affect how quickly the intensity of some effect will drop off as it passes through space, but or it can anyway. But it's not going to affect what we imagine is local, right? It makes it more difficult to imagine, but it's going to be basically the same idea. Is there a such thing as a single point in time? No more than there's a single point in space. It's possible, but again, we don't know, right? So I mentioned that the smallest distance we're capable of measuring is 10 to the negative 18 meters. Even the suggested smallest points in space and time, like Planck length and Planck time, they are so many times smaller, like millions of times smaller, right, than the tiniest distance that we can measure, which is already 1,000 times smaller than the proton. And so we are a long way from knowing whether or not there's a single point in space or time. So while it's possible, I wouldn't. I don't know. I don't think I could say yes or no to that question, and be lying, not be lying to you. So I'm going to refrain. Let's see. So it's not certain that fundamental particles have no volume. Yeah. So no, that, like I was saying, that we don't actually know what their volume is. We just know we have an upper limit on it, and that upper limit is small enough that we just assume they don't have volume, but they could very easily have a volume. And the real issue there is that um, the actual volume of the particle doesn't really matter all that much when it comes to quantum mechanics. Quantum mechanics is more concerned about the uncertainty in where the particle is than it is about how big the particle is. And so it makes a little more sense to define the size of a particle as the uncertainty in its location. And that can often be for example, say the electron could often be the size of the atom, which isn't very satisfying, right? But it is an extremely useful definition for size. And so eventually I want to actually do a video on this and talk about things like, why aren't electrons just little tiny black holes? And they aren't, right? But the question is, well, why aren't they? And I really want to do a video on that, but it's going to require a little more thought. So, yeah. Let's see. Yeah, trying to look for some other people here other than Tommy. He's kind of overwhelming the chat. Glad to have you here, but gotta tone it down a little bit. So let's see what we've got. We're stuck. Ironically, a way to think of it that's not even a little crazy. I know, right? Because I mean, whether or not there is, I assume this is in reference to what I said earlier about the quantum mechanical model, but yeah, I mean, we get stuck periodically, and that happens. We discover little things along the way, but we're stuck is something that is very important for the scientific community to admit, I think. And so it's definitely a fairly like sane thing to admit. But yeah, so I try to admit things when necessary. Let's see. How can one say the universe contains so and so X% of ordinary matter, Y% of dark matter, and Z% of dark energy? I think I read that backwards. But how can you express these not fully understood entities as a percentage? Okay, so I've talked about this in some of my cosmology videos before, but we have a lot of data from several different sources that tell us how much of stuff there is, right? So a lot of this comes from the cosmic microwave background, the CMB, but that data in connection with our models for cosmology allow us to make some judgments about how much stuff is in the universe without actually having to see it. So, for example, we know how much visible matter there is just because we can actually see it. It's visible. Then we also know how much dark matter there is based on its gravitational effect in galaxies, right? And how that affects the rotation of, the revolution of stars in a galaxy. And so we know how much of dark matter there is. And so then the question is, well, how much total stuff is there in the universe? And that comes down to the cosmic microwave background. And that tells us that the universe, that space in particular, is very flat, that it's very low curvature, like near zero curvature on the grand universal scale. We got little tiny things like curvatures around black holes and stars and planets and stuff. But if you're talking like cosmological scales, like distances between superclusters, we're talking like millions, hundreds of millions of light years, right? Maybe like 400 million, a billion, something like that, right? Very large numbers. On that scale, all of those little tiny curvatures around black holes and planets and galaxies and stuff, they're all really tiny. And so for the most part, there is zero curvature, near zero curvature across the entirety of all the space that we can see. And if all there was visible matter and the dark matter, the stuff that we're capable of seeing the effects of, the universe would not be zero curvature. It would be very curved. It would be positively curved, and it isn't. And so the only way that that's possible is if there's a third thing that we call dark energy. And we can calculate from our model exactly how much dark energy there needs to be in the universe in order to flatten it, in order to make it zero curvature. And so even though we can't see dark energy, we don't know what it is, we know that it has to be there, otherwise our model doesn't work. And our model works really well everywhere else. And so there's just sort of no way around it. And so we know those percentages. We know the percentage of ordinary matter and dark energy because of how our model lines up with the data that we can actually collect. So we can give you a rough percentage and a little pie chart and, make a little pretty infographic about it. We don't have to understand it entirely to know how much is there, is sort of the main point, the main takeaway. Let's see. Christoph says, is it possible to destroy a black hole? Maybe. The only way, well, I mean, not for us. We couldn't destroy it, but we could wait for it to destroy itself. It would take a long time, but theoretically, it is possible that black holes emit radiation, Hawking radiation as it's called, and because of that emission of radiation, they have to be losing their mass over time. The curvature around them needs to be going down, and that makes the event horizon shrink over time, very, very gradually. And so in order for a black hole to be destroyed, it's more like, we call it an evaporation. We say the black hole is evaporating. It's just an analogy, but it's just this very gradual shrink. It shrinks and shrinks until all the energy comes out of the spot that the black hole is in, and then the black hole's gone. So that's possible. Unfortunately, we've never actually detected Hawking radiation, so we don't know for sure that it's there. But the model that Hawking came up with for it says a lot of things about black holes that make a heck of a lot of sense. And so most people think that Hawking radiation is a thing, even though we've never actually observed it. Let's see what we got here. Is there any valid arguments that we exist inside of a black hole? I would say no. A black hole is a local phenomenon. It's not a global thing, and so black holes are not something that you see. They're not a phenomenon that you see in the cosmological model. They're only something that you can see in a local space-time curvature model, and so like you can't apply the basic quick facts that you know about black holes to the entire universe. It doesn't work that way. You have to consider the limits of the model that gave you those quick facts, and so I would say no, we are not inside of a black hole. Things would look very different, I think, as well if we were inside. So let's see here. Let's see. Space-time interval. I don't actually have a question there. All right. So is the space-time interval, say the distance between 0 and 5 stopwatch seconds of acceleration, less than the constant speed and longer for deceleration? Okay, so he's referring to a diagram that I think he sent me earlier. So let's pull this up. I think I can share the screen. Screen share. Share the entire screen. Can I not do that? Okay, so Chrome wants to share content what you would like. Okay. So you're going to get infinity for a second. So there goes some infinity. I apologize. All right. And so then here, hopefully everybody can see that. So right in here, this is a diagram. Space-time diagram in particular. Got the time axis on the vertical and the space axis on the horizontal, like a typical space-time diagram. And then you've got 3 different paths. Now this would look nicer if it was in color, but this curved path is a deceleration, right? So if you are stationary, you are moving straight up along the time axis, not back and forth because you're not moving in space, right? And so then a constant speed goes on an angle like this in a straight line. It wouldn't be the diagonal. That would basically be the speed of light. But then an acceleration is one that moves further and further in space over shorter and shorter amounts of time. Now, the difference here is going to be, I mean, these are 3 different paths, so it's kind of hard to compare them to each other, right? We run into the same problem with the twins paradox. But I mean, just based on deceleration and acceleration and constant speed, I mean, we're not going to get the same distance in the same amount of time, right? And so I would say no, that a 0 to 5 second stopwatch, right? Click 1, 2, 3, 4, 5, click, is going to give you different. It's going to give you different distances in space, and therefore different space-time lengths as well, space-time separations, or world line lengths, as they're sometimes called. And so because the time is the same and the space would be different, I would argue that the space-time would also be different between the 3 paths. You can't guarantee that they're the same space-time length without having them be the same path on the space-time diagram. Right? The rule that space-time itself is invariant, that it doesn't change from one observer to the next, is focusing on one particular path, right? One line between 2 different events. And if you've got 3 paths, like we got here, deceleration, constant speed, and acceleration, you've got, I'm going to come back to the screen here. Stop. All right. So on That no should be back to me, I think. I would say no. You don't have any kind of guarantees there. And distinctly, I would say no. They would, if you're talking the same amount of time for all three stopwatches, for all three timers, I guess they have to be in the same frame. But you count three, or say 5 seconds on the stopwatch, and you measure the distance traveled by each of those objects in your own measurement frame, then they're going to be different distances and therefore different space-time lengths. Little quickie at space-time diagrams, although that's hard to do without actually animating it. Let's see. How can the event horizon be a sphere when you can see all of its surface from any point you look at? Well, seeing depends on how light actually works, right? And so even though it's a sphere, it doesn't necessarily look that way because of the way that light actually works and travels through the space-time around the black hole. And so you can't use the same notions of that, right? I mean, you're not seeing the whole thing because it's flat. You're seeing the whole thing because light is spiraling outward from the event horizon, or from just outside it anyway. If it was at the event horizon, it wouldn't go anywhere. But it's very important to consider the optics that are happening around a black hole. And Derek from Veritasium did a great video on this when the black hole image came out I don't remember how long ago that was, a couple months. It was really good. Had a nice little demonstration to go with it. But it doesn't mean that that's where those things are. It's just where they appear to be, right? Optics are weird. Let's see. Center mass view. See. Oh man, this is the most active this chat has been ever, I think. I think some of you are new, by the way. Welcome. Let's see. Man, I'll pledge $10 next time. Yeah, so those of you who haven't looked at the Patreon rewards, if you pledge $10 per month or more, you get a guaranteed question at the beginning of the video. You don't get all of your questions answered. You just get one per live stream, guaranteed. I don't want the $10 questions to overwhelm the entire stream. But if you pledge $10 or more per month, you get the guaranteed question. Otherwise, I'm sifting through the questions in the chat, which I may not get to them all. There are quite a lot of questions. Do you use a Tarzan Boy instrumental for your outro in Science Asylum? No, I actually, with the exception of my intro song during the intro screen, which I made myself, by the way. The rest of the songs in the videos, including the outro screen, are available in the YouTube creator library. A couple years ago, YouTube made a bunch of songs available to creators, and so that we could have music in the videos. And so I use those. Eventually, I'm hoping that I can get my own made. I'll have someone I can pay somebody to actually make me my own songs, so that you don't hear the same music in other people's videos. I guess Cody's Lab has used some of the same songs that I use in their videos, and so people have recognized it, and that's always a little awkward. But that's the reason that I don't use one of those songs for the intro song. I wanted the intro song to be unique to my channel, and so I got one of those 10 by 10 box grid musical flash players or whatever, and I just set up a little pattern and recorded the audio. I am not a musician, so I'm not very good at that, but that's about. Let's see. Every time black holes collide, part of their mass is being destroyed. It's not actually being destroyed. It's being released, right? So you can't really talk about their mass. You kind of have to talk about the energy, right? So we don't tend to we tend to measure the mass of a black hole in solar masses and the number of times the mass of our own sun. And so that can be interpreted as a mass, or it can be interpreted as an energy, however you want to do it. But it's really just energy, right? And so black holes collide with each other, and the black hole that forms in the process has less mass than the two that made it, because a couple solar masses, right, a couple times the mass of the sun is going to get released as gravitational wave energy, and eventually, hopefully, arrive at Earth at some point. But so we can measure it. But it does get released. That mass gets released as gravitational waves, as energy in a wave. And so it's not destroyed. It's just a different type of energy now, right? Mass is a type of energy. It's sort of like a big, massive category. It's a little vague. It's not like kinetic energy or potential or something. It's kind of this. It's like sometimes those can also be mass. It kind of depends on the situation, whether or not we're going to measure it as mass or not. But conservation of mass isn't really a thing anymore since particle physics. So it's all about the energy. Wait, the black hole doesn't evaporate to a mass that's too low to maintain the state of the black hole? No, it will evaporate all the way until there's no mass left. Once the event horizon forms, it's a black hole. And even if it evaporates enough mass that it goes below, say, the upper limit, which is what, three times the mass of the sun, I think, even if it goes below that and the mass of the black hole is only 2 times the mass of the sun, it still stays a black hole, right? And so it requires more than that to be made, but if it evaporates, it can get under that over time. And eventually it could become a micro black hole that only has the mass of, say, an atom, and it's still a black hole. The thing is that the smaller it gets, the faster it emits radiation. And so as it approaches the scale of, say, the mass of a normal everyday object, it's only going to last a few nanoseconds more, and then it's gone, right? And so it's only evaporating slowly when it's the size of a star, when it has the mass of a star. And so when it gets smaller, a smaller mass, then it picks up the pace, and eventually, boom, it's just gone. Let's see, we're starting to run out of time here, but let's see. Space-time intervals are the same as world lines, though. Yeah, space-time intervals are the same as world lines. Sometimes world lines describe like all the way from the beginning of the universe to the end of the universe, but it's not really how they're used practically. You're usually measuring between 2 different events in a space-time diagram, so they end up being the same thing. Let's see. Let's see. There are no musicians here. I actually have some musician friends that would probably do it for me to make some songs, but I haven't worked up the courage to ask what their rates are yet. So the universe is expanding, then more vacuum energy will be there, right? So where does that energy come from? This is actually a very good question. I'm going to be addressing this in an upcoming video, maybe at the end of July. That's sort of the plan, but it might end up being August. I'm hoping for July. But basically, the idea is that energy is not always conserved, right? So according to our cosmological model, dark energy, what we're hoping is the vacuum energy, but we don't know for sure. The dark energy in the universe is a constant density, right? In the equation, that gamma, that cosmological constant that tells us how much dark energy there is a density. It's an energy density. And so the amount of energy in joules per cubic meter must always stay the same for dark energy. And so as space expands, as there's more space, it needs to create more dark energy in the process. And so there is more dark energy later than there was in the past, right? In the future, we'll have more dark energy than we did in the past and that we do now. And so energy is being created, and that's perfectly fine because conservation of energy isn't always true. I know, right? So it's only true when the time that you do an experiment, whether you do it now or 100 million years from now, doesn't matter, right? It's called time translation symmetry. And so it turns out that over time, because space expands and space-time warps and all this stuff, in general relativity, energy is not conserved, right? It's conserved in special relativity. It's conserved in quantum mechanics. It is not conserved in general relativity. And so it's perfectly fine that energy, dark energy, is being created over time, and that that's not violating any laws. So, fun fact. Let's see. Maybe just one more question, maybe. Let's see here. What's it's possible to set personal stream with private time? I've considered a personal live stream, but I don't know if I actually have the time for that. Even if I made it a super high roller perk, I need to make sure that I actually have time to produce the content that you're all supporting me for. And so I don't think I could set up private time. I would have too many things going on. I mean, a couple of years ago, I tried to do a podcast, and I realized 3 episodes in that I was just spreading myself way too thin. So I don't know. So I don't think that's gonna happen. Okay, so on that note, I think I'm going to be, dude, you have clones. Yes, I have clones, but they're kind of useless. I don't know if you've noticed. And in fact, sometimes they're around enough that I give them vacations, right? So you haven't seen Nerd Clone in a while because he got overworked a little bit, so I gave him a little vacation. But most of them are they're not useful for this sort of thing. So, and plus, if I'm doing a live stream, I'm not going to make my clones do the live stream. That's cheap. I'm not going to cheapen that. All right, so I think we're out of time here. We're like an hour, 10 minutes. It's usually where I stop. So, okay, so on that note, this has been the most active live stream we've ever had, and it's pretty exciting. Lots of stuff going on in the chat. Feel free to talk to each other in there if you want to. But I'm going to call it a day, and I will see you all hopefully at the end of July, and we'll have a good time then too. These are always a blast. So on that note, I'll see you next month, and thanks for coming, and thanks for all your support.